There's something that's quite shocking about the second law of thermodynamics. It's so utterly simple. After all, what could be simpler than saying that heat cannot flow by itself from a cold body to a hot body? It seems so obvious. And yet, from this very simple principle, it is possible to derive some very clever consequences. One of these will be the subject of this lecture. It'll be about the derivation of the Clausius inequality. So this is something like 150 years ago. One of the things that comes out of it, and there are many more, is that the entropy of the universe, and the universe could mean anything. It could mean our physical universe. It could mean a lot of different physical systems. It says that the entropy of the universe can never spontaneously decrease. Yes, it can remain the same, but it can never decrease. It can only increase. This and many other things come from simplicity, but with a very clever use of that principle. Let me begin by recapitulating some of the main ideas of the last lecture, which was on heat engines. So, here is a general heat engine with a high temperature reservoir that pumps in an amount of heat QH, H for hot over here. This heat engine then provides some useful work. We call that delta W. Some of that heat is used, that comes in. The rest of the heat gets wasted and goes to the environment, the low temperature reservoir as we call it. The amount of that is Q cold, and the amount of work that we get out is equal to the net amount of heat that we put in, delta Q, which is the difference between QH and QC. This, of course, is nothing but the conservation of energy, or the first law of thermodynamics. We define the efficiency of a machine as the work it performs divided by the heat it absorbs. So you have to provide it some heat, some energy, and that amount is QH. So when you do that division, so this is the net amount of work done, when you divide by QH, you get this quantity over here. Of course, this applies to every engine, but in particular, there is the Carnot engine, which has an isotherm here, so the temperature is constant from A to B. The volume has decreased from the value over here to the value over here. Then, in the second phase, the gas expands adiabatically, which means without loss of any heat to the environment or gain of heat from the environment, before it is compressed by a piston, and its volume decreases until one reaches the point D. All along this path, the temperature is constant. It's held in contact with the low temperature reservoir, so the temperature is T cold. And then the gas is adiabatically compressed by the piston, and it travels on this path. Again, this is adiabatic. Now you can use any substance that you like in this Carnot engine. It can be a gas of any kind, or it can be a liquid. But of course, it's much easier to do a calculation with an ideal gas, and so we considered an ideal gas, which was used as the working substance in this Carnot engine, where we showed that the heat absorbed, QH, during the first phase is equal to this quantity, nRT, multiplied by the logarithm of the volume here divided by the volume here. And so this is QH, correspondingly QC, that is to say, the heat rejected to the environment, is also proportional to the temperature, but to the temperature of the cold reservoir in this case, times the same quantity, log of VB divided by VA. In the earlier lecture, I had taken just 1 mole of gas, and so put n equal to 1 just for convenience. But you can see that wherever the gas constant R occurs, if you multiply by n, then you get the general result. In a little while, I'll again put n equal to 1 since we don't gain very much from it. The important point to note over here is that QH is proportional to TH and QC is proportional to TC. So the heat absorbed from a reservoir is directly proportional to the temperature of that reservoir. You can see that if we divide QC by QH, that's over here, then that's just equal to TC divided by TH. And now these over here are absolute temperatures for this ideal gas. And that takes us to a definition of the absolute temperature, which says that the temperature of reservoir number 1 divided by the temperature of reservoir number 2 is equal to the ratio of the heats absorbed from the first and the second reservoirs. This then enables us to simplify the efficiency factor over here as simply 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. Now, this eta, the efficiency, according to the second law of thermodynamics, always has to be less than 1. And so the second law of thermodynamics is telling you that Tc, the lowest temperature possible, can never be 0. Now let us come to the Clausius inequality about which I had talked earlier. First, I shall derive it, and in that derivation, its meaning will also become clear. So imagine some working substance. This could be an ideal gas, an actual gas, or a liquid, or whatever. And this system undergoes a cyclic process, which means that suppose this is the pressure, the volume, and inside is the temperature, maybe other variables. And so one starts from some pressure, volume, temperature, etc. at this point, and then as we proceed around the cycle, we go around until we come back to the original starting point. Well, of course, the temperature as we go around is different at different points. Now let me approximate the temperature between this point and a nearby point and call that T1. Of course, this point is supposed to be very, very close to here, but I've put it over here because otherwise you would not be able to see it. I'm going to then take a second point and a third point and a fourth, fifth, sixth, seventh point until I get back to the original. Now on each of these segments, the temperature has some value. Imagine now that there is a hot reservoir whose temperature is TH. This temperature TH is greater than the temperature of this working substance, which constitutes system S, and so TH is bigger than this or this or this or any of these temperatures inside over here. Next, imagine that I take a Carnot engine and allow it to work between these two reservoirs. There's the hot reservoir here and a relatively colder reservoir with temperature T1. Now this hot reservoir will provide a small amount of heat to this Carnot engine whose magnitude is delta Q1 and which flows into the Carnot engine. This Carnot engine rejects a small amount of heat, delta Q1, small q here, and it does a small amount of work, which we will call delta W1, which of course is just the difference between this heat provided and this heat rejected. I will do the same for every other segment. So now delta Q2 comes in, delta small q2 goes out, the amount of work done is delta W2, etc. And so in principle, for every segment, we have a Carnot engine which then works between the high temperature reservoir and these multiple cold temperature reservoirs. This is a very beautiful idea. It's a very strange idea, but this is the way that mathematical constructions are done. In our discussion of absolute temperature, we saw that the amount of heat absorbed is proportional to the temperature of the upper reservoir, and the amount of heat rejected is proportional to the temperature of the lower reservoir. So delta Q1 by delta Q1 is this, and so delta Q1 is obviously this. Of course, for delta Q2, the only difference is that we have 2 over here and 2 over here. And the same for all those n parts that we have created over here. Now think about the following. This system is receiving heat delta Q1 from here, delta Q2 from here, delta Q3 from here, etc. Of course, there is no second reservoir, so all this heat that is provided has to be converted into work. That work, which is done by the system, is therefore the sum of all these small delta Qs. So Ws, denoted here, is the amount of work done by the system. And this relation is simply the conservation of energy. Now let's look at the work which is done by all the Carnot engines. So this one does work delta W1, this does delta W2, etc. When you add them up, this is the total work done by all the Carnot engines. But now think about the following. That delta W1, so look over here, this is equal to delta Q1 with the big Q minus delta Q1 with the small q. The same goes for the second, for the third, and so forth. So, some work is done by the system, and some work is done by all these infinite number of imagined Carnot engines, which is here. Now, let us add the two works together. So the total work that's done is the sum of the work done by the system plus the work done by all the Carnot engines. So add this to this. But you see, delta Q1 comes here with a positive sign, here with a negative sign, and so the total work done is simply the sum of these, delta Q1 plus delta Q2, etc., etc. This is, of course, the total heat that is provided by the hot reservoir. We already have an expression for delta Q1, delta Q2, etc. So let's put that in over here. Take TH common, and we get TH into this factor over here, which is the sum of all the delta Qs divided by the temperature at which that heat was acquired. But now let's think about the following. This is the total work which is done, equal to this, but by the second law of thermodynamics, this cannot be a positive quantity. Remember that the Kelvin form of the second law of thermodynamics says that it is impossible to get work out from a single reservoir. So what does that tell us? Either the total amount of work done is equal to 0 or it is less than 0. Immediately that says that this quantity over here must be less than or equal to 0. But this TH, which is the temperature of the hot reservoir, is always a positive quantity. And so we arrive at this conclusion that the sum of all the delta Q's divided by T, the different T's, that sum has to be less than or equal to 0. Now, of course, I've drawn just 2 Carnot machines, but there are actually an infinite number of them. And so this quantity over here is, in fact, an integral in which the path ends back on itself. This here is the famous Clausius inequality. Now that we have this famous inequality, let us explore the consequences. Here's the mathematical form, but this is when the system is run this way. What if this is a reversible system? If it's a reversible system, then we can, if we want, run that system in reverse, the other way around. Now, the other way around means that all the heat arrows are turned the other way. So, delta Q1 becomes minus delta Q1, delta W1 becomes minus delta W1, etc. And so, what we find in running the system backwards is that this quantity here has to be greater than or equal to 0. If something is less than or equal to 0 and it is greater than or equal to 0, there's only one solution, which is that that quantity has to be exactly 0. For a reversible system, this has to hold true. Let's see what that means. From A to B, I can go along any path I want, and I'm going this way. But then I can go from B back to A by any other path that I want. And here, of course, the direction is this way. When I make this complete circuit, then the integral has to be 0. Now, in going on this path, I went from A to B and added up all the small amounts delta Q divided by T. In going from here to here along this different path, I went from B to A. That sum has to be 0. Instead of writing this again and again, let me put ds equal to delta Q by T, and then this relation over here becomes this integral of S from A to B plus B to A. Remember that these are arbitrary paths, and this point B can be here, here, anywhere on this plane. So the only way in which this relationship can be satisfied is by this being equal to this, and the other path yielding this. To summarize, the integral of delta Q over T, or ds, as we've written, from any point to another point is equal to the entropy at the final point minus the entropy at the initial point, and that is what we will call the change in entropy. Earlier, I had just stated this as a fact, but now we have proved that entropy is a state function, meaning that it doesn't depend on how you get to a particular point. The entropy will have a value independent of the path on which you traveled. That's a very beautiful and powerful result which holds for a reversible process. The Clausius inequality has led us to the conclusion that the entropy of the universe always has to keep increasing. And now let's see why. So here is our system. Here's the Clausius inequality. Let's imagine that we go from A to B by a reversible process. So we've gone this way. But on the way back from B to A, the process is not reversible. So I'll put in some gaps over here like this. And now let's explore the consequences. So in going from A to B by the reversible path, we got SB minus SA. That's for this path. Now for the irreversible path, I cannot write this as ds from B to A. I'm going to leave it as it is. This over here is S of B minus S of A, like here. And so what we found is that in going from B to A by this irreversible path, the Clausius inequality has given us this relationship. So this was here, and obviously when we take it to the other side, the signs change. In other words, the change in entropy in going from B to A is the final entropy minus the initial entropy, and that's what I'm calling delta S here. But what if this is an isolated system? In other words, there's no heat input, which means that in this system, which is now isolated and there's no high temperature reservoir, no environment, that means there's no delta Q1, delta Q2, etc. that is coming in. And so all these delta Qs over here are 0, which means that this integral has to be equal to 0. So if this is equal to 0, obviously delta S has to be greater than or equal to 0. This is telling us that when we have an isolated system, which means there is no outside and hence we can call it a universe, the entropy of that isolated system can not decrease. It can be equal to 0, maybe, but it can never be negative. That's an extremely important result. Actually, we've already seen it earlier when we considered an ideal gas which was confined to one section of a container, and then we allowed it to expand slowly. It did work on this piston, and finally reached this configuration where the volume increased 2 times. It doubled. In that case, we found that the entropy of the gas was R log of 2V divided by V, which is log of 2. But since this gas had done work on the piston, it had to take in heat from the environment, which meant that the entropy of the environment decreased and hence came with a negative sign. That change in the entropy of the environment exactly cancelled the increase in the entropy of the gas, which meant that the total change of the entropy was equal to 0. So, no change occurs in the entropy of the universe for a reversible process. Delta S is 0. But then we had also calculated in module 1.5 what happens when you suddenly remove this partition. The final state is the same, but because you remove this partition suddenly, no work was done by the gas as it expanded, and so no heat was taken in from the environment. In fact, no heat transfer occurs with the environment. This itself is the universe in that case. And so the total change in the entropy is positive. r log 2. And we've seen, therefore, that the entropy of the universe increases for an irreversible process. It is not zero, it is bigger than zero, because the log of 2 is a positive number, as indeed is r, the gas constant. From the Clausius inequality for a reversible system, we learned that entropy is a state variable, and we can use this very profitably. Just a quick reminder. Here is a system whose internal energy is U. It is supplied a small amount of heat dQ, and it does a small amount of work dW. Now we are taking a reversible system, in which case we will not make a distinction between delta and D. They're the same. And so delta Q is dQ and delta W is dW. Now, the first law says just this, that the increase in the internal energy of this system is equal to the heat received minus the work which is done by the system. This is just energy balance. But now for a reversible system, we saw that ds is dq divided by t, or you can write dq is equal to t ds in this way. And of course, the small amount of work which is done is the force into the distance, which can be written as the pressure multiplied by the small change in volume. This leads to the important result that du is tds minus pdv. Now let's choose as independent variables T and V to characterize the state of the gas. Of course, you can ask, could I have taken a different set of variables? Yes, we could have taken P instead of T over here, or we could have taken P and T. So obviously there's a matter of choice, but T and V are perfectly good variables to characterize the state of the gas. In that case, the internal energy of the gas is a function of the temperature and of the volume. And again, this is for any gas or liquid. We are not saying this is an ideal gas. When we make a small change in T and a small change in V, then the small change in U is just equal to the partial derivative of U with respect to T at constant V times dt plus the partial derivative of U with respect to V at constant T temperature times the small change in the volume. We will also write the entropy as a function of the temperature and the volume, which means that the small change in entropy upon changing the temperature slightly and the volume slightly is this. And just to save space, I have not written, but it's understood that this is the partial derivative of S with respect to T at constant V, and this is the partial derivative of S with respect to V at constant temperature. So now let's put this into the first law. So I'm going to take du from here, put it here, and now this is equal to T, which is from here, multiplied by ds. ds is this, so that's this part, and there's of course minus p dv. Remember that in this equation, dv and dt are independent of each other. That means that I can, if I want, put dt equal to 0 and then see what this equation says, or I can put dv equal to 0. This is the meaning of independence. And so quite obviously, when I put dv equal to 0, I get this relationship. When I put dt equal to 0, then I will get du by dv at constant t is equal to t into ds by dv at constant t minus p, which is here. These are two independent relations, but let's simplify a little more. Remember that the specific heat at constant volume, or the heat capacity, is how much the internal energy changes when you change the temperature at constant volume. That means that this first relationship over here becomes ds by dt is equal to Cv over T. So then this relation over here becomes this, and this obviously is then simply this. Just take T on the other side. These are formal relations, but very important in applications. Let me now develop more implications of the fact that the entropy is a state variable. Let's use the mathematical fact that partial derivatives commute with each other. In other words, I can differentiate with respect to y first and then with respect to x, or first differentiate with respect to x and then with respect to y. So let's use this and the relationship that we just derived, du is equal to T ds minus P dV, to prove what is called the Maxwell relation. Now, there are other Maxwell relations too, and in studying thermodynamics, it is sometimes quite puzzling as to what one is taking as independent variables or as dependent variables. We can, if we like, write U, the internal energy, as a function of T and V, but can we also write it as a function of the entropy and the volume? Can we write the entropy also as a function of the volume and the temperature? Or the pressure as a function of S and T? The answer is yes. In fact, we've already done a calculation in which we could find the entropy, or rather the change in entropy, when we change the volume or the temperature. And so certainly S is a function of volume and temperature. And so the temperature can be expressed in terms of S and V. Therefore, you can write this U over here as a function of S and V. Now the dependence of U upon temperature is certainly there, but it is through S. So now in proving this Maxwell equation, let's look at the steps involved. First, consider U as a function of the entropy and the volume, in which case, obviously, du is then du by ds at constant V plus du by dV at constant S. If we compare this form du with the earlier form du, which was T ds minus P dV, like over here, then obviously the coefficients have to be exactly the same. So T is the same as this, and minus P is the same as this. Now let's use the commutativity of partial derivatives. And so if we differentiate U with respect to S first and then with respect to V, or with respect to V first and then with respect to S, we should get the same thing, in which case dt by dV will be d by ds of minus P. Remember that this minus P is the coefficient over here. So this was du by dV, and now we're differentiating this with respect to S. Means that dt by dV can be written as this, obviously. The only thing to figure out is what is being held constant over here and over here, because when we take partial derivatives, we have to make sure that the correct quantity is held constant. So, as step 2, let us decide on the correct independent variable. Remember the equation of state, which related P, V, and T together. Of course, for the ideal gas, that is PV equals RT. So one relationship between three quantities. For a real gas with interactions, it'll be more complicated, but again, it will be one relationship between three quantities. And so the temperature is expressible as a function of the pressure and the volume. So here what we have, dt by dv, is actually dt by dv with the pressure being held constant. Of course, here we can express P as a function of S and T as well. And so what we have here, dP by ds, is actually dP by ds at constant temperature. This means that this relationship has now taken this form with the pressure being held constant here and the temperature being held constant here. Now, of course, you remember from basic calculus that dy by dx is equal to 1 over dx by dy. This relationship holds for partial derivatives equally. And so we have achieved our goal of deriving the Maxwell relation, which is here before you. One last example. Here, an arbitrary, any heat engine operates between two reservoirs, each with heat capacity C. The first has initial temperature TH and the second has TC. The engine operates until both reservoirs reach their common temperature, which is called TF. So here's a picture that we can make. This is not a Carnot engine, any engine. As heat flows to this machine and waste heat exits the machine, work is performed. We are asked to show that the final temperature has to be greater than the square root of the two initial temperatures. And in the second part, find the maximum amount of work that can be extracted. Well, let's begin by remembering that for a reversible process, ds and delta S are indistinguishable and ds is simply dq divided by t. Now dq is simply c times dt, and so ds is equal to this. This is for the infinitesimal amount of heat that has flowed. To find the finite change in entropy, we must simply integrate from the initial temperature, which for the upper reservoir is TH, to the final temperature, which is common to both reservoirs, and do the same for this one. So here we will integrate from TC to TF, and of course this is a trivial integration. It is simply C times the log of TF over TH plus C log TF over TC. When you combine them, it's this. The heat capacity is obviously a positive quantity. Now, the second law of thermodynamics says that for an isolated system, delta S must always be greater than or equal to 0. And if you consider this entire system, the two reservoirs and the heat machine, well, that's the universe, that's the isolated system. And so the second law is saying that this delta S must be positive or 0. Then log of this must be positive, which means that this quantity here must be bigger than or equal to 1. If it's equal to 1, then we have delta S is equal to 0. And so we have this condition that TF squared must be greater than or equal to THTC, and so we get the final temperature of the two reservoirs, they have equalized now, will be greater than this quantity, square root of TH into TC. The equality will hold if this X is a reversible machine. Finally, let's find the maximum amount of work that can be extracted. That happens for a reversible process, in which case TF is equal to this. Of course, then we simply use the first law. The work that comes out from here will be equal to the total heat absorbed minus the total heat that's rejected. The total heat absorbed will be C times the change in the temperature of the upper reservoir minus the expelled heat, which is this. So when you add them up, you get this. Put in TF equal to this, which means that the work obtained from this machine will be equal to this. Here I've put it in the form of a total square, and that makes clear that we get a positive amount of work out from the machine.